Hello, this is Jack Jackson. In this video, we're going to talk about iterated integrals over a general domain and talk about how to set these up. We'll look at a few examples. So, we have already seen in the previous videos that we can view a double integral as an iterated integral, and because of that, we can apply the fundamental theorem of calculus along with calculus 1 and 2 integration techniques to evaluate the integral exactly. But so far, the domain was a rectangle, which led to constant limits of integration on both of the integrals. In this section, we'll see how to set up and compute iterated integrals over more general, non-rectangular domains. So here's some examples of what the domain might look like. This first one here that you see pictured here is this with in between these two parabolas is a type 1 region. The top of the curve is given by a function of x, in this case g of x equals 5 minus x squared, and the bottom is given by another function of x. In this case, f of x equals 3x squared minus 2x minus 1. So notice that these curves can be solved for y equals some function of x. And if we think of a vertical strip going from the bottom of this region to the top, it's always bounded on below by this first function and above by the second function. Both are functions of y in terms of x. Okay, so that's what we call a type 1 region. A type 2 region is sort of backwards from that. This one over here on the right with this blue background is a type 2 region. If we think of a horizontal strip going here, it's always bounded on the right by this curve here, which is x equals a function of y. So you can solve it for x in terms of y. And then this side here, you can solve this for x in terms of y as well. And we have a region here. If we were to try to do this one with a vertical strip, notice that over here, say in this region here where I am, then we see that the top and bottom are given by this curve, and then the same curve down here, which would have a different formula when you solved it for y in terms of x, and then here we would have different top and bottom boundaries here. But we have a consistent right and left boundary when we go sideways. So that's a type 2 region. Sometimes you can get a region that's neither type 1 nor type 2, like the interior of this funny looking shape here. And the way to handle that is you have to partition it into smaller regions. So we break this, say where I've drawn these little curves in the middle here, say pretend those are vertical lines, then this region here might be described with this curve on top and this one on the bottom. A type 1 region, this might be a type 1 region. This could be a type 1 region here, maybe here and here. So these could be a bunch of type 1 regions or perhaps type 2 regions, depending on how we think of it. When you do this, say if we break this into 1, 2, 3, 4, 5 subregions, then it's going to end up with 5 integrals. Integral over each piece, and then add those up. So let's take a look at an example here. We have the function f of xy is 2 times parentheses x squared plus y. We want to integrate that function over the region bounded by y equals 2 minus x squared and y equals x. So we have this function f of xy equals 2 times x squared plus y, and it's in the first quadrant for the domain. It's bounded by the domain is bounded by y equals 2 minus x squared and y equals x. So the first thing we want to do is to graph the region that makes up the domain. So let's do that first. This is pretty straightforward to do this. So here's a graph here. Here are the curves. Here's y equals x, this line here. Here is the other curve, y equals 2 minus x squared, and of course we have the x equals 0, the y equals 0, the x-axis, x equals 0, the y-axis, excuse me, which is right here. And over here you have the region in the first quadrant that's shaded. So that's the domain. Any xy ordered pair in here is going to be in the domain. So obviously not a rectangle. One of the first things we need to do is find the boundary points, find the corners of this region. Of course, they're not too hard to tell by looking at the graph here, but what we're actually doing is solving some systems of equations. So, for example, to find this point down here, we want to know that x equals 0, so it's on this vertical line here, and y equals x here, where those two things cross, which of course is at the origin. And then we want to know up here when x equals 0, and we're on this curve. So here we have x equals 0 and y equals 2 minus x squared. Plug in x equals 0, we get y is 2, so we get xy equals 0, 2. Easy enough to see that. Over here we want to know where these two cross, so we're solving y equals 2 minus x squared and y equals x simultaneously, and also x is positive because there's another place where these two cross over here, which is not really relevant to us. So let's see, what can we do? We can replace the y by x here. So we got 2 minus x squared equals x. Solve this by getting everything on one side, 0 on the other side. Eliminate some things here. So add x squared to both sides and negative 2 to both sides. We get x squared plus x minus 2 equals 0. We factor that pretty easily as x minus 1 times x plus 2 equals 0. This means x minus 1 equals 0, which is x equals 1, or x plus 2 equals 0, which is x equals negative 2. But x is positive, so that eliminates this one. That's, of course, this point down here. The one we have left is x equals 1, y is the same, so xy equals 1, 1, which, of course, we could have seen from the graph as well. But we may want to find those, well, we definitely do want to find those boundary points. So we have some boundary curves and some boundary points, and now we want to set up the integral. The easiest way to set this up is to think of a vertical strip. So if we take a point A down here and go up to the point B as a vertical strip, the bottom of this is always on this curve y equals x. The top is always on this curve y equals 2 minus x squared. No matter where we put that strip, if we move it from over here on the left or to the right, all the way across here, the strip is bounded by these same curves. And furthermore, those are already solved for y in terms of x. So this is set up nicely for a type 1 region. It is a type 1 region. And so here's how you set the integral up. You start by setting the integral of the first integral up on the inside. Now, since we have a vertical strip, we're going from a lower y to an upper y. We're integrating with respect to y first. Okay? And so the lower y has a value of x. The upper y has a value of 2 minus x squared, regardless of where this strip is. But of course, those values depend on what x is. So we have variable lower and upper limits. Of course, the function we're integrating is f of x 2 times x squared plus y. And we're integrating with respect to y. Now notice when you're finished with this, you will end up with a function that is a function of x alone. Now we integrate with respect to x, and the x runs from 0 to 1. When you set up an iterated integral in this manner, the inside integral will have variable limits. The outside integral will have constant limits. The inside integral, if it's with respect to y first, these limits on that integral must be in terms of x. Formulas involving x only, functions of x. And then the outer limit will always be constants. If we had a type 2 region, for example, we would integrate with respect to x first, then these would be functions of y. and then dy on the outside, and these would be constant functions of constants of y for y limits. Okay, so now let's go ahead and evaluate the integral. Now this is kind of like a calculus 1 integral, except that we treat x as a constant when we're finding an antiderivative. So it's a partial antiderivative. And so I went ahead and distributed the 2 and just made this a polynomial, 2x squared plus 2y. 2x squared is treated as a constant, so an antiderivative there would just pick up a y as a factor. And then we take the antiderivative of the second part. It's a power function. So the power goes up 1 to 2, divided by the new power, which is 2. So 2 divided by 2 is 1. You could double check that by doing a partial derivative with respect to y. Partial derivative with respect to y is when this is just y times something, it's that coefficient is the derivative. And over here, the power rule, 2 times y to the first power. So we can see that that is the correct partial antiderivative. So its partial derivative is what we started with. Okay, just evaluate that from the endpoint. So we're basically using the fundamental theorem of calculus, just like we did back in calculus 1 or calculus 2. So the way that works, remember, is we take this function here, evaluate at the top limit, minus evaluate the bottom limit. Now these are y equals, so we substitute for y. The x's are left alone. So this is 2x squared times, well, where the y is, put 2 minus x squared here, plus y squared, so where the y is, put 2 minus x squared. And then minus, and do the same thing with x's in place of the y's here and here. Alright, now let's just do a little algebra here. I'm going to distribute here. 2x squared times 2 is 4x squared. 2x squared times minus x squared is minus 2x to the fourth. I'm going to square this out. Square the first, you get 4, that's here. Square this is positive x to the fourth, that's here. Multiply and double for the middle term, and you get minus 4x squared there. Here I'm going to distribute the negative 1 and also do a few combining things here. So x times x squared is x cubed, then distribute the 1, that's minus 2x cubed there. And then this minus and plus, that makes minus, and that's x squared. Combine some like terms here. Let's start with the x to the fourth. Minus 2x to the fourth plus 1x to the fourth is minus 1x to the fourth. Yeah, there's an x cubed term there, minus 2x cubed. Let's see, there might be some x squares. There's a minus 1x squared, minus 4x squared plus 4. Okay, so 4x squared minus 4x squared is 0, minus 1x squared is minus x squared. And it doesn't look like there's an x term, but there's a constant term of 4. Okay, so now we just have a pretty easy calculus 1 integral to do. Just integrate this. So the powers all go up by 1, and you divide by the new power. X to the fifth, divide by 5, so that's negative 1/5 x to the fifth. That goes up to the fourth power. 2 divided by 4 is 1/2, negative because of the coefficient there. That goes up to the third power, so we got negative 1/3 x cubed, and then the 4 picks up an x, so 4x. Evaluate from 0 to 1 means take this formula here, put 1s in place of all the x's here, minus, put that in parentheses, minus, parentheses, put 0s in place of all the x's here. The good news is this last part with all the zeros just wipes out to 0. And of course 1 to any power is 1, so that makes this a little bit easier to do here. So we just negative 1/5 minus 1/2 minus 1/3 plus 4, and then the rest is all 0. And you can add those together. You can do it by hand, get a common denominator, or I used a calculator. 89 over 30. Divide that out, it's 2.96 with the 6 repeating. Here's a TI Inspire cast working the thing out completely, and the way we do that on the TI Inspire cast is, let me just show you. So the way this works on the Inspire is we pull up our menu here and our templates, and you see the one for the integral right here. Click on that. The outer integral is going from 0 to 1, and that outer integral is with respect to x. Then the inner integral, the integrand is itself an integral, because it's an iterated integral. So the inner integral is going from x up to 2 minus x squared. And we're going to evaluate that at 2 times parentheses x squared plus y, I believe it was. Yeah. That integral on the inside is with respect to y. And we can evaluate that exactly. And then I can say, I can take our answer here and approximate it in a decimal form like that. And so that's how I got that particular screenshot. And so there, if you see that, you see it does agree with the work that we did by hand. Okay. I want to show you what would happen if we were to try to do this one with the integration the other way around. Okay. Now it is possible, but it's considerably harder to do this the other way. We can set this up with respect to integrating with respect to x first, and then integrating with respect to y. To do that, we're talking about horizontal strips. But if you look, the left or lower end point of our horizontal strip is always on x equals 0, but the top of the strip depends on where you are, whether you're above or below y equals 1. So we're going to have to break this at y equals 1 into 2 regions. Now each of the two regions is a type 2 region. So each one of those will have to be a separate integral, and then we add those two integrals together. When I say a separate integral, I mean an iterated integral for each piece. Okay, and then the other difficulty we might have is we have to make sure that these equations that give these curves have to be solved in the form of x equals a function of y. In this case, we can do that. In some cases, that's not really feasible. All right, so if we think of a horizontal strip going here, we have to break this into 2 integrals. One where the y's go from 0 to 1. That's over this triangle here. And the y's going from 1 to 2. That would be over the region up here. So in this bottom region where y's go from 0 to 1, the outer limits are 0 to 1. The integral on the outside is derivative is a dy. It's an integral with respect to y. So the inside is the integral with respect to x. Where does x run from? Well, on the left it runs always at 0, so that's a constant function for that side. But on the right side it always goes up to this red curve. Well, that red curve is y equals x, or x equals y. And so the x value there is the same as the y. So you need these formulas, remember, now have to be in terms of y if you're integrating with respect to x first. So after we do this integral on the inside, we have only a function of y. Okay, similarly, when we do the one up here, we go from 1 to 2. The strip going from left to right here will always be at 0 on the left. But now we go over to this curve here. Well, this curve, remember, was y equals 2 minus x squared. We have to solve that for x. So let's see, that gives us x squared equals 2 minus y. So x will be plus or minus the square root of 2 minus y. But where we are in our region, x is always positive. So it's always x is the positive square root of 2 minus y. And so that becomes the top there. So this one was not too much difficulty in solving this in terms of x. That is one of the places where we could run into a real problem is we do have to solve for this so that these our limits are in terms of y only. All right, let's see if we can work it out this way. All right, so here we go. I went ahead and distributed the 2 and did this as an integral with respect to x. So it's very similar to the way we did it before. It's just a polynomial, so that x squared goes up to the 3rd power, divide by 3, so that's 2/3 for the coefficient. So we've got 2/3 x cubed plus the y here just picks up an x, and we still have our 2 here, so this is 2xy. We evaluate on our limits from 0 to y. Similarly over here, we get the same antiderivative, partial antiderivative, 2/3 y, 2/3 x cubed plus 2xy, but now we want to evaluate this from 0 to square root of 2 minus y. In both cases, of course, evaluating is just plug in the top number minus plug in the bottom number. In both cases, the second part is 0, so we just have the first part, which is in this first integral, it's 2/3 y cubed plus 2y squared. In the second one, it's 2/3 times the square root of 2 minus y to the 3rd, or 2 minus y to the 3/2, probably be a better way to write that. And over here we get 2y times this square root. Now the one on the left here, the first one, where we're integrating from 0 to 1, that one is just a polynomial, so it's pretty easy to find the antiderivative there. Y cubed becomes, so you add 1 to the power, that's the 4th power, divide by 4, 2/3, and divide by 4 cancels the 2, so you get 1/6 there for the coefficient. The y squared here becomes y cubed, divide by 3 is 2/3 for the coefficient. So the antiderivative there was 1/6 y to the 4th plus 2/3 y to the 3rd. We want to evaluate that from 0 to 1. I'm going to hold off on evaluating for just a minute. On the one on the right, we need to do a substitution. U needs to be 2 minus y. And so that makes du minus dy. Notice that you can also solve this for y since this is linear, and we see that y is 2 minus u. Notice also if y equals 1, we can plug this in and u becomes 1. And if y is 2, we see that u is 0. So when we change this to derivative with respect to u, we see that the limits are going to go from u equals 1 on the bottom to u equals 0 on the top. Now, the dy is replaced by minus du. So we have a du here. The minus I put out the front. The 2 minus y is replaced by u. So this is u to the 1/2 to the 3rd. That's u to the 3/2. So this is 2/3 u to the 3/2. This is u to the 1/2. But now we still have this y. This is where it's useful to solve this thing in terms of y in terms of u and get y equals 2 minus u and plug that in. So it's a little more complicated type of substitution than you do at the very first of Calculus 1, but certainly you did things like this either later in Calculus 1 or in Calculus 2. Distributing here, we get distribute both the 2 and the u to the 1/2, so we get 4u to the 1/2, and we get minus 2u to the 3/2. Here I brought the minus in and I combined some like terms. So 2/3 u to the 3/2 minus 2u to the 3/2 is negative 4/3 times the negative 1 is positive 4/3, and then that's u to the 3/2. And then we have now this is now minus u to the 4u to the 1/2. All right, we finally got this down into where we see it as just a sum of power functions. So now it's pretty easy to find an antiderivative. You add 1 to the power. 3/2 plus 1 is 5/2. Multiply by the reciprocal. 2/5 times 4/3 is 8/15. And u to the 1/2. Let's see, we add 1 to that. 1 plus 1/2 is 3/2. Multiply by 2/3, that's negative 8/3 there when you multiply by the negative 4. And now we're ready to evaluate that from u equals 1 to u equals 0. These are u values. Over here on the first one, these are x value or y values, excuse me, from 0 to 1. So now let's evaluate. So we take this formula here, 1/6 y to the 4th plus 2/3 y to the 3rd. We want to evaluate from 0 to 1. We put in a 1 minus, we put in a 0. Let's just look at that part a minute. 1 to any power is 1, so this is 1/6 plus 2/3 and then minus 0. On this one, when we plug in 0 for u, it's the first part that becomes 0. And when we plug in 1, we just left with the coefficients. We do have the minus there, so this is minus 8/15 and then plus 8/3. Then get a common denominator there of 30, and it's not too hard to do that by hand. We get 89/30 or 2.96 repeating. Here's the CAS, TI-inspired CAS solution over here, and once again we get that. Notice that's exactly the same answer that we got when we did it before. However, this way was a little bit harder. So we get the same answer either way. But one way or the other might be harder when we reverse the order because of several things. Number one, it may require the integral to be broken up into different integrals. That makes it a little bit longer or harder. One way may be harder or even impossible because it does require solving the boundary curve for a specific variable. In this particular case, not only was it a type 1 region, which made it easier to set up by integrating with respect to y first, the curves were given in the form of formulas of y equals some function of x. Doing it the other way, we had to solve them. Sometimes that's very difficult or even impossible. Okay, and another thing is, once we get the integral set up, it may turn out that one integral is more easily worked out than the other one. So that makes a difference too. So if you can do both ways without much difficulty, then you could possibly do both ways, and then that gives you a check. But in practice, most of the time, what we're going to do is just pick the easiest way and work it that way. Let's look at another example. We'll pick this one up in our next video.